And we're on to actually start.
Yeah, take it away.
Cool. All right, thanks, Yov. And hello, everyone. Picked a good day to present, it looks like. So I just wanted to discuss some of our efforts on diagnosing animation smoothness. I presented on this topic in the past. We talked about it before. And I linked to the previous presentation where we talk about motivations and give some examples. But today I wanted to sort of dive a little bit deeper and showcase how things actually work, at least in Chromium, and explain why that influences our thinking. So no talk on animations is great without some nifty animations, but since I dared not cast them over video, here's just a photo of the most popular animation I could think of. For those who don't know, this is a poster circle, and it was, I remember being deeply inspired in sort of compositor-driven animations and CSS animations back in the day. So some of the topics I wanted to chat about today were just a quick background on the problem. I want to look under the hood, at least for Chromium, and then my team's efforts in the space, and then help and feedback wanted at the end. All right, might as well dive right in. So hopefully the broad definition of animation smoothness is somewhat intuitive, the goal being to show every single visually complete animation frame, or to put it more plainly, no jank. But the specifics of how exactly to measure that can be a bit elusive. And essentially, we'll have to dive into the details involved there. So for now, note that there's sort of two distinct tasks to get started. So the first is just identifying missed animation frame updates. And the second is identifying expected animation updates. And we'll get to those in a second. So why even work on this? So very common feedback from developers includes the following. So for one thing, a replacement for RAF polling to diagnose main event loop hiccups. So RAF polling, for those who don't know, is using request animation frame API to continually ask for animation frame callbacks, count how often those actually get fired as compared to the expected number, and sort of guess how often the main thread, therefore event loop, was blocked, preventing animation frames. Now, the act of RAF polling has implications on performance and measurement, so it's not a good idea. It's a bit of an anti-pattern. But for lack of an alternative, it still gets done. And so often we hear about folks doing it only periodically to take a sample just to get at least an estimate. And so this was kind of one of the design goals for the frame timing API. We often want folks to better understand the performance of scrolling, to get better insights, or at least to know when it is a problem, when is scrolling janky, folks would like to know. There's also broad confusion about something we call checkerboarding, which is, the page is often split up into tiles, and everything on screen is nicely rendered. Things that are off screen may or may not be rendered or discarded. And if you scroll very quickly, you might see sort of blank portions of the page show up. And folks often say, why is my page broken? Is it my framework? Is it this or that or whatever? And there's no real insight to know that this is just, the GPU is just trying to catch up with rendering what was already previously rendered. And there are things developers could do to lessen the likelihood or increase the likelihood of those things happening. And there's broad confusion. Often we see reports, folks don't even know that that's the reason. And another very common thing is, oh, hey, we just did this big revamp. We added a bunch of animations. We want to do big, rich transitions in response to the user interaction. What effect did this have on UX? Is it even running smoothly? Is it useful for users? Is it doing well? And of course, sort of as browser and animation framework implementers, are our changes making the right improvements? So most of these questions are not possible to answer with web platform APIs today. It can even be sort of exceptionally difficult to diagnose locally with detailed instrumentation. So if we have time, I'd be keen to learn about any tools or tactics folks in this room are aware of today, or you could just reach out to me later. But hopefully I could provide at least some clarity about how we tend to do it. Now, obviously, I will have to skip over many important details today. So here's just a few links that go into detail if you want to read up on it later. All right, so let's look under the hood, at least for Chromium. This is the simplest view of the path a single frame takes through the sort of multi-process and threaded architecture of Chromium. On the left, we start with vsync. This is a platform signal specific to display hardware. It could have a fixed frame rate, a variable frame rate, and even an adaptive frame rate. And the GPU process gets the signal, and then it decides if a frame is needed and worth attempting. Pages aren't always in the foreground. Sometimes the GPU is busy. We're already sort of have back pressure, but most of the time we request from the renderer to begin creating a new frame. Now within the renderer, the layer compositor gets the signal and it starts updating its internal data structures. There's a bunch of input that could be directly driven on the compositor thread. And much like the GPU could decide not to start a frame, the compositor could decide not to start a main thread. But typically, it sends that signal. So it sends a signal to the main thread to begin main thread. And now in parallel, both the compositor and main thread are trying to produce a frame. The main thread event loop could be experiencing queuing delay due to tasks. And then there's a lot of work that goes into painting. So I'm skipping over all of the details here, but this is typically when you look at breakdowns within DevTools or other things, like a lot of focus goes into this main thread update portion of work. So eventually, the renderer gets a signal that the main thread is ready to commit. The two threads come together, all the data structures get merged. We raster a bunch of textures that moves the pixels to the GPU. And there's this extra step of activation because in the compositor, we actually have copies of data structures. And so we have to move things from the sort of temporary working copy to the live copy. That gets submitted to the GPU. The GPU has to draw everything, swap thing. And if we did that all before the vsync timeline or deadline, that's when a fully completed frame is presented. Okay, and we'll have to run along. I know it's complicated. Some of the videos do better. So there's many reasons why we may not complete all of these steps within the allotted time to present a fully formed new frame. Here's just one very common example. The main thread update takes too long. So what happens here is the compositor sets a time limit for the main thread update. And if that limit is exceeded, we still go ahead and we still update the frame with the latest compositor update only. We will use the previous state from the last main thread update if we have one. So the key point being that we will still produce a new frame update. It might not have all of the rendering changes. Eventually, in the future, that main thread update will complete, we hope. And whatever active compositor update at that time is available, it will pick up those changes and they'll get shown. So we very often see a steady stream of partial frame updates. That's what we call this when the compositor provides an update without a main update. How do you account for that? There is a steady stream, but it's just not fully complete. And what happens if that late main update actually ends up with no rendering changes at all? Okay, there was no update even desired, in which case all of those past partial updates, they're actually visually complete after all. Okay, we only know that in hindsight. All right, so how do we account for that? Or what if there was a visual update from the main thread, but it wasn't an animation? What would that look like to the user? So you're just loading some content into some placeholder. You're attempting a visual update, but it gets delayed by a frame or two. For the user, it just looks like any other loading flow. Okay, the delay visually to the update is identical to delay from the network or processing or rendering. It's not really what we call an animation jank. And sometimes, there really is a visual update, and that update really is an animation, and it really is delayed a frame. So is that jank? Even there, it depends. What if we get a new but slightly delayed frame update, but we get one steadily every single frame? All right, so there are frames generated in parallel. They're all delayed, but there's still a steady stream. What does that look like to the user? If that animation is being driven by user input, it might feel a little bit less sticky, like a scroll driven by a finger. But if it isn't input driven, it might look perfectly buttery smooth. It just happened to start a frame late. All right, so there's lots of nuance into turning all of this detail into somewhat of a summary. Okay, so let's look at some real examples. All right, to do so, we're going to use a tool called tracing. There's a new tool called Perfetto, but for today, I'm going to focus on the old one, tracing. For anyone not familiar, tracing is sort of the raw signals that tools like DevTools use underneath the hood. Anytime you do like a performance recording, it gathers a bunch of trace events, and then it sort of displays in a custom UI. But you could actually record your own traces with your own categories and go right to the source and show them. So I linked a few things here, and I have some tips in the notes. So this is what a sample rendering trace might look like. And it shows some of the breakdowns between these different processes and threads. At the top, we have render main thread and some of its tasks and their breakdowns, and then compositor thread and its tasks, GPU, vsync, all that stuff. So there's a bit of a pipeline here that with like messages sent across these boundaries. And it could be quite daunting to follow, especially as things get busy. So for that reason, there's been a longstanding effort within Chromium to help simplify the diagnostics here. So I like to think of it as sort of squashing the layers. So in Chromium, we produce something called a pipeline reporter trace event. And from here on in this talk, this is kind of what I'll be focusing on. So if the previous slide was confusing, that was just to confuse you on purpose. So pipeline reporter events describe the path of a single frame end to end. You can see the duration it takes for any stage within that pipeline, and therefore you can begin to make conclusions about which frames of updates arrived on which vsync boundaries. You can learn if frames ended up with no useful updates at all, or when a useful update came too late and ended up completely discarded. So as a quick note, in order to report this summary correctly, we have to actually wait kind of for the future before reporting about the past. So it makes it a lot easier to look at traces that were recorded in order to make them understandable. But just know that when you see some of these things reported, they weren't actually known at the time that they were reported, if that makes sense. Also, for anyone who will dig in here, a bit about naming. Some of these breakdowns have long-winded names like submit begin mainframe to commit. That's just basically saying from the point in time where we submitted the begin mainframe call until we started committing. And so it's the time in between those two. But I linked to some of the docs earlier that go into greater detail. Okay, so at the start, I said there are two tasks at least just to get started. The first was identifying animation frames, and so that's what we just talked about. But the second is identifying expected animation updates. That's because, as I said, a missed frame with no update, we don't really consider a jank. So some animations are obvious and sort of easy to define, such as scrolling or CSS animations. RAF-driven animations are more conditional. The mere act of creating a callback, a request animation callback, it's not really sufficient to prove that there's a running animation. It depends on what happens within that callback. And at least in Chromium, we're trying to detect sequences of direct style updates on animatable properties of elements. Okay, so kind of style, like direct JS-driven animations. This is not my area of expertise, so I linked to a document that goes into much greater detail. So if we were to select any of these pipeline reporter events within a trace, you'll get a lot of metadata. I think I'll skip some of this, but it tells you the frame sequence and what active animations we're running. And this is very useful. And so if pipeline reporter events know about the animations that were active, we can also sort of flip the script and look at the active animations, which know about the frames that were produced. All right, so there are these events called frame sequence trackers, and you'll get the type of frame sequence, which is basically the type of event, and all the frames that were generated. And so if you dive deep, you'll be able to look at the details here. So here we have a touch scroll animation, and we could see how many frames were expected over the duration of that scroll, and we know how many were actually produced. So in this case, 5 frames were dropped according to this particular definition. So one interesting detail here, this animation took over 4 seconds. And if we assume 60 frames a second, we should probably expect 245 frames. But we actually see 125 are expected. And I would ask the audience to guess, but I'll say it's because it's driven by your finger, and your finger isn't always necessarily moving a sufficient amount to produce a new frame. So it really depends on how fast you're flicking, if that makes sense. All right, so with all of that background, we can begin to focus on the definition of a drop frame. It's certainly used widely among graphics folks here. So historically, I think this name came from a literal state of an animation frame. You can have a drop frame, a partially produced frame, a fully presented frame, no update desired. But the term is sort of evolving to this broader concept of identifying imperfect frames in ways that matter to users. All right. So we can use these pipeline reporter breakdowns to start to piece together this puzzle, this timeline puzzle of drop frames. And I touched on some of the ambiguity, but I'll try to repeat and introduce more. So we have, we have partial updates where we know we have a stale main, but we produced a new frame with some new thing. What happens if you're rapidly scrolling and it's a perfectly smooth scroll and some of the main frame update is lagging? Is that even, detectable by a user? Does it matter if the scroll is very, very slow, if it's creeping or if it's flinging? There are nuances there. What if you're dropping frames during animation idle periods? There could be other updates happening that could be interesting. There could be other pages that are sharing a renderer process that have updates that are interesting. And then another topic is you can have perfect animation smoothness. Every single frame is presented exactly complete and on time, but you could still have poor animation quality. A simple example here is video. So we can have a video that is producing every single frame on time, but the actual bit rate is really low. There's poor network quality. The user isn't impressed with the actual quality of the video. Another example there was shared to me by Microsoft. Some edge engineers were working on scrolling, and in their attempts to make scrolling buttery smooth and always instant, they sort of parallelized enough in the compositor that it stopped being sticky. You would have this jitter where the main certain updates would not be in sync with others, and you would have the page sort of jittering around. So it's perfectly smooth, frames were generated, but it wasn't what users expected. Users preferred a slightly less performant scroll that was consistent and sort of visually stable. So it's a trade-off. Animation impact area. Some animations are tiny little icons in the background that are barely noticeable, even if you do a recording and look at them in slow motion. Others are full bleed, obviously important. And that's related to this broad concept of, from a UX perspective, who's to know which animation is important for the user? It's tough. All right, so for all these reasons, conceptually, it seems that drop frames isn't really a Boolean value. It's not that a frame is dropped or not. It's a bit of a fractional value. It might even be worthwhile to consider it a probability that it mattered to the user. So we know that there are missing updates, and we know there was an active animation. That's not what is a probability. It's just the likelihood that this was actually noticeable jank for the user is a probability. And so when you diagnose real live pages, we find small imperfections are plentiful, okay? Even in the smoothest, best sites that users rate, there are still examples of poor performance. But because not all of these imperfections are necessarily noticeable for users. So now I personally doubt that there's a single correct answer for how to interpret that data and turn it into a summary, okay? If your goal is to track down pixel perfection, I think you will want to know every single detail about drop frames. If your goal is to identify top user pain points from a slew of field data, that's a very different story. Hopefully that makes sense. Okay, so quick recap before we move on. Every frame may be fully presented, partially presented, dropped entirely. There may be any number of active animations which require an update from either place. Even fully presented frames may have other rendering issues, such as checkerboarding or video quality or that sort of thing. Some animations are trickier to track than others, and user expectations for animations are trickiest of all. So hopefully now we can talk about why something like frame timing v1 we feel probably doesn't cut it. At the very earliest motivations for frame timing v1, as I understand it at least, they included understanding animation performance, especially things like scroll, but it's really evolved towards just providing data about browser event loop. There's no coverage for compositor updates as far as I'm aware, which is where many important animations like scrolling tend to happen. There's no notion about active animations at all either. So while there's certainly value in understanding browser event loop, we already have long tasks, and we have event timing, and we have element timing, which cover presentation times for specific key moments. Which is why we think we're seeking an alternative to frame timing v1, at least. We discussed that a bit last year at TPAC. I suspect we'll want to continue to discuss it this year. So in case I haven't convinced you that it can get tricky, here's a screenshot of how things tend to look on real life sites. So tracing UI will create sort of a new row every time it needs to make room for overlapping events. And here we have at least 6 rows created, because many parts of this pipeline can happen in parallel. There are always frames in flight, okay? New compositor updates might start while we still have pending main updates. As you saw, the GPU could be working to show the last update. We could start multiple main thread updates even within a single vsync in case we get an even newer update within deadline, especially if you have an old stale one that just finished. We might want to start a new, just to try to get a quicker sequential update. And then somewhat specific to the way Chromium reports these events, you can have copies of these things just because the trees tend to fork, and so you just need to duplicate some of the breakdowns. So all this to say, Pipeline Reporter was added to simplify things, but it's still very complicated. So some of my own experiments are focused here. So how do we take these live traces from real sites, convert all the Pipeline Reporter events into a single simple timeline, best as we can? How do we convert that, like all those individual data points, into a rolling score over time, and then try to convert that timeline, which has a bunch of detail, into a single summary, okay? All right, so visuals. So here's a graph. This is some of the post-processing that I've been working on, which shows the different signals you could look at, different animations, different frames, different criteria. So here's sort of the large red area is when we know we have missing main thread updates during main thread animations. Sort of the yellow line is similar, but it ignores when you have a smooth compositor-driven scroll, where we think maybe the main thread update isn't visible. The much less large blue tracks the lack of even a partial frame update, so the lack of compositor-driven animations, so the inability to show an expected compositor animation. And then the green, which is almost invisible in this particular example, is checkerboarding. So the question is, was this example a smooth experience? So if you look at a recording of what this actually looked like, there were visible hiccups early on, but they felt very much just like loading issues. And then later on, scrolling was actually very smooth. And maybe there was a lack of timely main thread updates, but they certainly weren't noticeable because scrolling was smooth and that's what the user was doing. So in this particular timeline, there's plenty of imperfection, but the page experience of this example actually felt pretty good to users. It's pretty tough to draw conclusions. On the other hand, this is an example where there's just tons of nuance. There's tons of simultaneous issues of all kinds, the extent of which appears less than before, but actually this flow felt worse to users, okay? Because some of these signals are more important to users than others under certain criteria. And as a small aside, there's this big spike at the end there, but that was actually from like an Android notification tray being swiped down. And so maybe there was a blip on the screen, but users probably weren't paying attention to the actual page update when that happened. And so we try to combine these signals using different weights and different criteria. And so at the top, you have the breakdowns. On the bottom, you have sort of a merged timeline. Unfortunately, this has to be a bit opinionated since the relative value of each of these signals will differ. And the merged graph has scores, if you notice, that they lie kind of between the extremes of each of the signals. And then we could try to convert that timeline into a single score. And again, this kind of has to be a bit opinionated, and we're not even close to sure what the right approach is here. So we're trying a bunch of things. This is just a couple of examples of like reducing that timeline into a single score. So in Chrome today, if you use Canary, you could find this flag where you can ask to display a performance HUD. Not only will it show you live Core Web Vital scores, there are some early experimental definitions for some different ways of considering drop frames. So the way we detect animations continues to evolve. The way we turn those into the definition of a drop frame continues to evolve. And then the overall turning it into a single score, all of that continues to evolve. But it's still sort of fun to play with these early revisions, just to open sites, interact with them, and see these numbers change and see if it matches expectations. So the numbers appear to be percentages because they're in the range of 0 to 100, but they're somewhat magic list numbers for now. We also have some early entries in sort of Chrome UKM data, which is our field data collection. Yeah, the definitions don't necessarily match all of what I mentioned today yet. They continue to evolve, but just pointing this out. And then there's also some integration already with dev tools to displaying timelines. So if you do performance recordings, you'll see the frames displayed, but then they're also color coded according to the statuses, like what's in there. So again, not all of this matches all of the nuance that I mentioned today, but these are fun toys to play with. Okay, net. The interpretation of these timelines, I think, depends on your goals. As I said, evidence of some dropped frames is pervasive in live sites. And if your goal is to be pixel perfect, I think you need to very carefully locally instrument. You need to use tools like what I showed today. And so hopefully I gave you a few new tactics to play with. But if your goal is to understand field data, I think that we need a lot of simplification and generalization. And I think we still have a lot left to learn. So we are playing with our own experiments here to try and understand what our own expectations are. But this is an evolving process. Now, last time I presented, Ryosuke asked a great question, specifically around why are we focused on drop frames, especially in a world with like variable refresh rates. Shouldn't we be striving to produce frames as often as possible as opposed to failing to produce when we try? And it was a very good question. And I think that we often have been talking about it in terms of percentage dropped. So for every attempt, was it successful or not? And then turning that into sort of percentage. And the reason we think about it that way is because idle time we consider good, like it's fine. Idle time is smooth. And so percent dropped is kind of like frames per second if you're playing a game. It's really a 1 second rolling average of how many times a new update was presented. But even within games, there's a trend towards more accurate measurements, like frame to frame delay. And this is, you could take the maximum frame to frame delay within a second or the average frame to frame delay. And so, if you just look at FPS, you might have 60 FPS that drops down to 55. That could look different. That could be 5 frames equally dispersed within that second, or it could be 5 frames in a row, which was very obviously a long latency for a new frame update. And so if your goal is to ensure that every animation update takes no more than, say, 10 milliseconds of latency, which would be a crazy high goal, but if that's your goal, I still think you probably want to identify animations, ignore animation idle periods, still solve these nuances of what do you do with partial frame updates for compositor-driven animations and what's important for users. But then you could take this data and interpret it in a way where your goals are a lot higher than things. So this is where there's differences of opinion. I think it'll depend on your outcomes, if that makes sense. But I think a lot of the groundwork is shared no matter how you interpret the results. Okay. All right, now we get to how we can help and hopefully some discussion today. So first of all, I said frame timing V1 is not sufficient for measuring animations, but is there still some strong desire for better diagnostics specific to main event loop processing? I would love to know that. And then I talked about how animation smoothness only during animations could miss other downsides of skipping rendering, such as progressive loading or responsiveness. But I think these are already covered more directly by existing perf APIs, like event timing and element timing and long tasks. So do folks agree? Is that good? Is that separation of concerns agreeable? For the other implementers, I've tried to investigate as much as I can, but I'd love to know if there are any surprises, if breakdowns are significantly different, if we need to change entirely the way we're thinking about this. So the more we can learn quicker, the better. And then for field data consumers, how much detail do you want? How much simplification do you want? Would you use this to do like deep debugging, or do you just want a summary of user pain and that sort of thing? And so where do we find balance, and how do we figure that out? And with that, that's all I have for today. Thank you very much.
Thank you, Michael. Let me stop the recording and we can then discuss.